Welcome to Physics 2211, Lab 4, Oscillations. The goals for this lab include calculating the motion of a spring mass system oscillating in two dimensions, as well as demonstrating the energy principle by comparing the transfer of energy between kinetic and potential energy. I found that the spring mass system is not fully isolated because some of the energy is lost between the kinetic and potential energies in the experiment compared to the isolated model. Key concepts include Newton's second law, which states that the net force acting on an object is the change in momentum over the change in time. The velocity and position update formulas are related and incorporated into the code. The second key concept is the energy principle, which states that the change in energy of a system is equal to the work done on the system by the surroundings, plus the transfer of thermal energy between the system and surroundings as heat. The change in energy is a result of the difference in energy between the initial and final state. The model will assume the transfer of heat is negligible. To calculate the total energy of a system, the net force will be included in the system instead of work in the surroundings as potential energies. The total energy of the spring mass system is a combination of kinetic energy, gravitational potential energy, and spring potential energy. The spring is modeled oscillating in two dimensions. The system is the force of gravity on Earth, the spring force, and the kinetic translation of point mass. Because all the forces are contained within the system, the surroundings are nothing, which means the change in energy of the system would be zero if the transfer of heat is assumed to be negligible. The net force is a combination of force of gravity and the spring force. By combining the kinetic translation of point mass with the changes in spring and gravitational potential energy, the transfer of energy within the system can be graphed. The weight of the spring mass is 0.4 kilograms, and the initial position and velocity was calculated using the first frame step in tracker. The initial conditions also include the spring constant and its relaxed length, which were solved shown to the right. The system energies are computed between kinetic energy, gravitational potential energy, and spring potential energy. In the calculation loop, the initial energies of the system are set. Then the gravitational and spring force are used to update velocity and position. And before calculating the energy changes, the positions and direction of the spring is updated. Here is the model running. The blue ball is the model, and the red ball is the actual path from the tracker data. Comparing the x and y positions of the oscillating spring mass graphically, the model and experiment align similarly. However, the y position data is less related than the x position data. Because the spring mass system is not isolated in reality, some of the energy is lost due to its surroundings, which weren't able to be modeled, hence the differences between the graphed model and the experiment. The model also assumes that the spring mass is a point mass at the center of the attached weight to the spring. In reality, the spring itself also has a mass. Finally, there is a possible error in the accuracy of placing the point masses in tracker. For the model, is the energy principle satisfied? Yes, the energy principle is satisfied because the change in total energy remains zero the whole time, while energy is constantly being transferred between kinetic and potential energies. No energy is gained or lost to the surroundings. I used the y component of position to calculate the oscillation period for the model. The x component of position has its own oscillation period as well. The spring stiffness calculation is not the same between the oscillation period for x and y position. Therefore, these two estimates would affect the spring mass's system's motion based on the spring stiffness used. Comparing the x and y position data, when you look at the spring stiffnesses, you can see that the x position spring stiffness would be about 6 newtons per meter, while if we use the oscillations from the y position data, the spring stiffness would be 6.83 newtons per meter, which is a considerable difference. Thank you.